morning everyone, welcome to this GCSE Chemistry live group tutorial. I hope you all had a really great weekend and welcome back to the first of our tutorials this week. We've got quite a busy timetable coming up, so I hope you're looking forward to the sessions we're having this week. Today's is GCSE Chemistry and the topic is masses and moles. So lots of you have joined us before and know how these work, but I'll just give a quick rundown for those of you who don't. So this will be an hour-long session, so it will finish at 10:45, and the session will be led by our chemistry tutor Aman, who lots of you know already. Aman studies medicine at King's College London and has been a tutor with us for a really long time, completed over 150 lessons. So it should be a great session today. The session will go on for 1 hour, as I said, and there'll be time at the end for any questions from you guys. So you can use the chat or the Q&A function in the webinar and just put any questions you have for Armin there, or for myself. I'm Tilly and I work at my tutor. So today's session is going to be quite a mathsy session. So if you guys could make sure you have a calculator on you, I'll just give you a moment to grab one of those because there'll be quite a lot of questions that will require a calculator. We're going to do more sort of questions and exam style questions today. So just make sure you've got one of those. And if you want to join us for other sessions, just a reminder, we've got other subjects going on this week. We've got maths, we've got history, biology, physics, English, and potentially a couple of other ones later in the week. So if you want to join us for those, just check out the My Tutor live lesson timetable on our site. Cool, so if everyone's ready, then let's get started.
Welcome back everyone, and as Tilly said, if everyone could make sure they've got a calculator, because today and this week, in fact, we're going to be covering the quantitative side of chemistry, or the numerical side, starting off with masses and moles. And if you don't like maths, this is probably quite a tricky topic, but if you do like maths, then maybe this is the nicer side of chemistry. What I would say is that today's session in particular is going to lay the foundations for what you need to know to be able to tackle the maths type questions in chemistry, and then the later sessions of this week will be building on that. So we're going to start off with relative atomic mass. So if you've been here before, you may remember on the periodic table, we talk about the atomic mass being the top number, or the relative atomic mass being the top number. And we've said that that is the number of neutrons plus the number of protons. When we do mathematical chemistry questions, we take the relative atomic mass to mean something else. Effectively, it's kind of the weight of the atom. But remember, atoms are really, really small, so we don't know, we can't really use their actual weight in exam questions because they would be too tiny. So we use the relative atomic mass and we compare to carbon. And the reason we compare to carbon is because carbon is one of the even atoms. It has 6 electrons, 6 neutrons, and 6 protons. So every atom is compared to the mass of carbon. So if carbon has a relative atomic mass of 12, that means hydrogen has a relative atomic mass of 1, and so it is 1/12 of the mass of carbon. So effectively, they're compared to carbon, all the atoms are. So that's the first thing. And the second thing is, I remember sometime last week, someone asked me, why on the periodic table does chlorine have an atomic mass of 35.5? We can't have half a neutron or half a proton, so why is that? And that is because we have something called isotopes of elements, and that is where elements can exist with different numbers of neutrons, and the key thing is it's always a different number of neutrons. So for example, chlorine exists as a 36 and a 35, and they are in 50-50% abundance. So there are 50% with 35 and there are 50% with 36. So that means on average, the relative atomic mass of chlorine is 35.5. Now we do need to know how to calculate the relative atomic mass when there are lots of different isotopes. And on the screen, you can see the calculation for that. So we take the percentage of isotope 1. So if we take our chlorine example, that would have been 50%. We times by the relative atomic mass, that was 35. Then we add that to the percentage of isotope 2, which was 50%. We multiply by the relative mass, which is 36, and then we divide the whole thing by 100. So to practice that, let's do 2 examples then. Before we go on to those examples, does anyone have any questions about that calculation at all? Okay, so let's go on to rubidium then. So we've got rubidium, it's got one isotope that has a relative mass of 85 and an abundance of 72.7. Someone's asking, do elements always have the same number of protons? Yes, the number of protons don't tend to change. And remember, they're always equal to the number of electrons unless the atom is charged. So the rubidium calculation then, we've got the first isotope has a relative mass of 85 and an abundance of 72. Abundance just means the percentage in the Earth. So here we've got 72%. We times that by 85. That's the first isotope. Then we add it to the second isotope, which is rubidium isotope 2, a relative mass of 87 and an abundance of 28. So 28 times 87. And then we divide by 100. Now, before I put that into the calculator, or any of you put that into the calculator, what we can see is we're expecting the number to be closer to 85. And the reason for that is that there is more of the 85 atom, because there's 72% of 85, but only 28% of 87. So statistically, we're expecting it to be closer to 85. So does anyone have the answer for that one then? On their calculator? It's okay if not. So if we add that up, oh, okay, we've got some answers coming through. 5.56, so it's 85.56. Excellent, well done. So we usually give to 3 significant figures. So in this case, it would be 85.6. Great, well done. Okay, so the second example is copper isotopes. Well done to everyone giving me their answers. That's exactly correct. Someone is just asking me, what do you mean by carbon being used as the reference point? So remember I said that atoms are really, really small, so we can't take their actual mass when we use it, when we do calculations. So we take a unit or kind of a proxy for their mass. So we say that carbon-12 is quite an even atom. It's got 6 protons, 6 electrons, and 6 neutrons. So every atom is compared to carbon-12. So we say that if carbon-12 has a mass of 12, hydrogen is 1/12 of that, so it's got a mass of 1. And chlorine is 35, so that means it's, as a fraction, it's 35 over 12 of carbon. So everything is compared to carbon, and that's just because we need a reference point, because we're using a relative atomic mass. It's not the actual mass of the atom, we're using a relative mass, so that means you need a reference point. Okay, so let's do the copper isotope one then. So copper isotope 1 has a relative mass of 63 and an abundance of 69. So that means the first one will be 69 times 63. We then add that to the second isotope, which has a relative mass of 65 and an abundance of 31. So 31 times 65, and then we divide by 100. Again, does anyone have the answer to that one? Excellent, 63.6 to 3 significant figures. Someone's asking, could you do 0.69 times 63 plus 0.31 times 65? Yes, that would, you would then not need to divide by 100. Okay, well done. So that's the first thing. So relative atomic mass, and this is really key in a lot of questions. You get 2 marks for calculating things like that. And just make sure when you're doing it that the abundances add up to 100. So you can see here, 69 plus 31 makes 100, 72 plus 28 makes 100. Okay. The next thing then is the relative formula mass. So the relative formula mass is all the relative atomic masses of a compound or molecule added up. So we've calculated how to do the relative atomic masses. In questions, they usually give you the relative atomic masses unless they're specifically asking you to use isotopes to calculate it. So here it's asking us to calculate the MR, the formula mass of magnesium fluoride. They've given us the compound is MgF2, and they've given us the relative atomic masses. So all we need to do is add up the atomic masses of each element. So magnesium has 24, so we do 24. Fluorine is 19, but there are 2 of them, so we do 19 plus 19. And as someone rightly said, the answer is 62. So well done. So that's the formula mass. So the way I think of it is it's a formula. If it's a compound, we've got a formula there. Don't forget, it could also be O2, because that's also technically a formula or a molecule. So well done everyone that's telling me 62. Okay, calculate the MR of calcium nitrate. So this is slightly more tricky. So we've got calcium first, which has an atomic mass of 40. We then need to multiply everything in the brackets by this 2. So N times 2, so nitrogen times 2, so 14 times 2, which is 28. We've then got 3 oxygens times 2, so that means we're going to have 6 oxygens, so it's 16 times 6, which is 96. So 40 plus 28 plus 96 for calcium nitrate. So it's really important when you get brackets that you multiply it all out. So everyone that's saying 164, you're exactly correct. It's not a minus outside the brackets. Sorry, that's just saying these are the relative atomic masses over here. That's not a minus. Okay, so well done. So we now know how to calculate the relative atomic mass and how to calculate the relative formula mass. Before I move on then, is everyone happy with that? Just because these are kind of the basics for being able to do the question. So we need to make sure we're happy with these questions. Okay, let's move on. So next we're moving on to moles. So 1 mole of a substance is its AR in grams. Remember, AR is the relative atomic mass. So it's the relative atomic mass in grams. So for example, 1 mole of magnesium, which has an atomic mass of 24, is 24 grams. So it's just the atomic mass in grams. So remember I said the atomic mass doesn't really have a unit. We're comparing to carbon-12, we're giving it a mass, but if we want to put it in grams, we put it in moles. So we say that 1 mole is its AR in grams. Now, you do need to know what Avogadro's constant is, and it's 6.02 times 10 to the power 23. And that says that 1 mole always contains the same number of atoms, molecules, or ions. So 1 mole of magnesium contains this many atoms or ions. 1 mole of oxygen will also contain that many. 1 mole of fluorine, 1 mole of sodium. So 1 mole always contains the same number of atoms, molecules, or ions. So calculate the mass of 0.25 moles of carbon dioxide. So before we go into calculating the mass, we need to know the main equation that's being used. And it's really important that we're all quite happy with this equation. So for people that are sending me answers, we'll go through it in just a second. So this equation here is one of the main equations that's used at GCSE Chemistry, and this is that the number of moles equals the mass over the atomic mass. So just to show you that as a triangle, because I know a lot of you like to use triangles, number of moles equals the mass, I'm going to put that in grams, over the molecular mass or the formula mass, AR or MR. So that's that in a triangle form. So the question here says calculate the mass of 0.25 moles of carbon dioxide. So we've been told the moles, we can calculate the MR because we've been given the relative atomic masses and we want the mass. So if we have a look, to get the mass then we need to rearrange that equation. So if we look at our triangle, if we cover up this, that means we need to do moles times the molecular mass or the formula mass. So here, number of moles is 0.25. We then multiply it by the relative molecular mass. So carbon dioxide has a relative molecular mass of 12 plus 16 plus 16, and that's because there's 1 carbon and 2 oxygens. So 12 plus 16 plus 16. And then we multiply that in, so that's 44. So 0.25 times 44, so it's 11. That's 11 grams is the mass of carbon dioxide. Okay, is everyone happy with that one there? That question? Everyone that gave me answers, well done. You got it correct. Okay, so no questions about that one. All right, the next example then says, how many moles are there in 25 grams of sodium chloride? So now we're going back to our original question or our original equation. Number of moles equals mass over the atomic mass or molecular mass. So the number of moles then, so remember they haven't given us the number of moles, we've been given the grams, so we know that's 25. So we're going to do moles equals 25 grams. And then we're going to divide by the relative atomic masses. So if we have a look, the relative atomic masses, in sodium is 23, and in chlorine is 35. So 23 plus 35 is 58. So the number of moles will be 25 divided by 58. So what's that? .43, excellent. Well done. Someone's asking, is the moles different when substances are different states? No, so remember when we change states, the number of atoms isn't lost. So if we go from solid to liquid, the number of particles there stays the same. So no, when we change states, nothing changes with regards to the moles. Good, so yeah, the answer is 0.43. So we did 25 divided by 58. Well done. And you can abbreviate moles to MOL. Okay, the third question says, calculate the mass of 1.7 moles of potassium manganate. The relative atomic masses are there. So again, we're calculating the mass, so we need to use that the mass equals moles times the AR or MR. So here, the moles then, so 1.7, we times by the relative formula mass. So what's the relative formula mass of potassium manganate? So potassium is 39, we add that to 55, and then we do oxygen times 4, so that's 64. So yeah, 158, well done. Okay, so 158 times 1.7, and so the answer will be 268.6. Well done. Good, so it's 268.6 grams. And again, if they don't give you a way to kind of, if they say not 3 significant figures or 2 decimal places, always assume 3 significant figures. So in this case, then it would be 269 grams to 3 significant figures. And if you remember to put in brackets to 3 significant figures, then it just helps the examiner know that you know what you're doing. Okay, excellent. So before we move on, is everyone happy with that equation then? So we've calculated the atomic mass, we've calculated the molecular mass. Is everyone happy now that to calculate the number of moles, it is the mass over the molecular mass or the atomic mass? Okay, I'm going to take that as a yes. No one's asking me any questions. All right, so stepping it up a little bit more then. So now we need to know how to calculate the masses from equations, and this is where it can get a little bit tricky. So we know how to calculate the mass of just one element or one compound, but what about when we're using an equation? So if we look at this question over here, it says we've got a balanced equation there. So magnesium plus water goes to magnesium oxide plus hydrogen, and we can check it's balanced. There's 1 magnesium on both the reactant and the product side. 2 hydrogens, 1 oxygen, 1 oxygen. So we've definitely got a balanced equation. It says 1 gram of magnesium is used. What is the mass of magnesium, or the maximum mass of magnesium oxide that is produced? So we know that we've got 1 gram of magnesium, and we need to know how many grams of magnesium oxide is produced, and we've been given the relative atomic masses. So what we do is we start off with how we did the previous questions. So we use our equation of moles equals the mass over the MR. So if we want to calculate the number of moles of magnesium first, because we have the grams there, then we just do 1 divided by its AR, and its AR is 24, or its relative atomic mass. So the number of moles of magnesium equals 1 over 24. And then we can use our balanced equation to work out the number of moles of magnesium oxide. Because remember, in balanced equations, we can see the ratio of reactants to products. So if we have a look at magnesium, we can see that there's basically a 1 here. Well, that's what there is, even though that we don't write that. That means there's 1 magnesium, and it forms 1 magnesium oxide. So the ratio of magnesium to magnesium oxide is 1 to 1. So that means if we react 1 over 24 moles of magnesium, we are going to form 1 over 24 moles of magnesium oxide. So if we want to calculate the mass of magnesium oxide, all we need to do is rearrange this equation over here, which says then that the mass is equal to the moles, so 1 over 24, times the MR of magnesium oxide, which is 24 plus 16. So the Mg is 24, the oxygen is 16. So that would give us 40. So we do 1 over 24 times 40. So what's the answer then? What's the maximum mass of magnesium oxide that can be produced? Excellent, 1.67 to 3 significant figures. Really good, well done. Okay, so that was an example then of how we use an equation to calculate a mass. Well done for everyone saying 1.67, you're exactly correct. Okay, let's do the second question then. Before we move on, does anyone have any questions about that specific example that we went through? Okay, so a student wanted to make 11 grams of copper chloride. The equation for the reaction is below. Okay, someone's asking me how many marks would a question like this be? So it ranges from 3 to 4 marks. So if, for example, I'm going to show you an equation in just a second where you would get 4 marks. So this one would be 3. And the reason for that is that the ratio is 1 to 1. If the ratio is something like 1 to 2 or 1 to 3, that means we have to change the number of moles. So just to go over that a little bit more slowly, we calculated the number of moles of magnesium to be 1 over 24. And remember, we did that by taking the mass and then dividing by 24, which was the relative atomic mass of magnesium. And we looked at our reaction and said that there's 1 magnesium produces 1 magnesium oxide. If, for example, when it was balanced, this was a 3, that means for every 1 magnesium, we produce 3 magnesium oxides. In which case, if there was 1 over 24 moles of magnesium reacting, that means we would produce 3 times this, so 1 over 24 times 3, which would be 3 over 24, 3 over 24 moles of magnesium oxide produced. So then, instead of doing 1 over 24 times 40, you would do 3 over 24 times 40. Someone's asking, is the masses from equations harder on higher papers, or is it like the example given? So the questions I'm doing right now are the same for both foundation and the higher tiers. We will be going on to higher tier questions on Wednesday. Today, we are doing what's found in both papers. In the higher tier paper, this would be found maybe towards the beginning or middle. In the lower tier or foundation tier papers, it would be found nearer the end. But we all need to know how to do these using the equation moles equals mass over the molecular mass. And remember, this is a key equation. So if you can remember this one, it will mean that you can do lots of different questions. Okay, so let's do the second one. A student wanted to make 11 grams of copper chloride. The equation for the reaction is below. So we can see that copper carbonate plus hydrochloric acid goes to copper chloride plus water plus carbon dioxide. The relative atomic masses are given. Calculate the mass of copper carbonate that the student should react with dilute hydrochloric acid to make 11 grams of copper chloride. So it's exactly the same as the previous question. We've been given a mass of something that we don't want. We want the copper carbonate, and we want to know the mass of copper carbonate. So again, we can use the number of moles to help us. So if we calculate the number of moles of copper chloride, we can then use our equation to see the ratio to calculate the number of moles of copper carbonate. So copper chloride has a mass of 11. So the number of moles equals 11 over the MR, so the relative formula mass of copper chloride. We've been given the atomic masses. So it's 63.5 for copper plus chlorine times 2. So and chlorine's got 35.5, so 2 of those. So what is the number of moles then of copper chloride? So if we type this into your calculator, what's the number of moles of copper chloride? Great, so someone's saying 0.08 moles. Excellent. Is everyone happy with that being 0.08 moles? Yep, good, okay. So it's 0.08 moles. So then if we want to calculate the number of moles of copper chloride, of copper carbonate, we know that in the reaction, there is 1 mole of copper chloride, or 1 copper chloride, that is formed from 1 copper carbonate. So if there are 0.08 moles of copper chloride, that means there are 0.08 moles of copper carbonate. So if we want to calculate the mass, all we need to do is use this number of moles. So remember, the number of moles equals the mass over the MR. So if we rearrange that, that means that the mass equals the number of moles times the MR, So if we do the MR of copper carbonate, then it's 63.5 plus carbon, which is 12, plus 16 times 3, which is 48. And if you type that into your calculator, you should get a mass of 10.1 grams. Excellent, well done. Is everyone happy with that? So again, we start off by calculating the number of moles of whatever compound they've given us. So they will give you a mass of something. We then use the equation to see how many moles, or what's the ratio of what we want. If the ratio is 1 to 1, the moles stay the same. If it's 1 to 2, we double. If it's 1 to 3, we triple. And then we multiply that by the AR or the MR to calculate the grams or the mass of whatever it is we want. Okay, let's do the third question then. Iron 3 chloride. So remember, this 3 is like last week we covered this. So transition metals can form different ions. This is saying that iron forms a 3+ ion in this case. So iron chloride can be produced by the reaction shown in this equation. So this is our iron chloride here. It's saying that we add iron and chlorine to form iron chloride. Calculate the maximum mass of iron chloride that can be produced from 11.2 grams of iron. So we're looking at iron and we're looking at iron chloride. So first of all, what do we need to do? What's the first step that we need to take then? So we've been given a mass of iron. We want the mass of iron chloride. What's the first step that we take for this question? Yeah, work out the number of moles. Okay, so what's the number of moles of iron then? So remember, the number of moles equals the mass over the MR. So we've been given a mass of iron of 11.2. So it's 11.2 divided by the MR or the AR, which is 56. So 11.2 divided by 56. So what's that? Great. It's not 112. So whoever's saying 112, it's not 112. And the reason for that is we ignore anything in front of our atoms or our compounds. It's always what's actually there. So Cl2 here, we would multiply Cl by 2. But in iron, there's only one of them. So we don't multiply that by 2. All right. Yep, so everyone that's giving me an answer there, well done. It is 0.2. Excellent. Okay, so 11.2 divided by 56 is 0.2. So 0.2 moles. Okay, so how many moles are there of iron chloride then? If there are 0.2 moles of iron, how many moles of iron chloride? Excellent. Someone's telling me 0.2. Brilliant. And that's because it's a 1-to-1 ratio. Very well done, everyone. So you can see here, there's 2 moles of iron and 2 moles of iron chloride. So that means it's a 1-to-1 ratio. So if there are 0.2 moles of iron, there are 0.2 moles of iron chloride. So what's the mass then of iron chloride? So first of all, what's the MR of FeCl3? So we multiply this by the MR. So 56 plus chlorine times 3, so 35.5 times 3. So what is the MR first of iron chloride, and then what is the mass? So the MR of iron chloride is 56 plus 35.5 times 3. Excellent. And then we multiply that by 0.2, and someone is saying to me that that is 32.5 grams. Good, well done. Everyone happy with that question then? Yep, 32.5. Excellent. Okay, well done, everyone. So that's 3 questions there that we've done on moles equals mass over the molecular mass or the relative formula mass. So what we've covered so far, we now know how to calculate the relative atomic masses, the relative formula masses, and the masses from equations. Can you write down the formulas to work these all out? Yep, so the main formula is up the top there. So it's the moles equals the mass over the formula mass. What I can do for you is I'll write down a step-to-step method for calculating these equations. So the first thing that you want to do is calculate the number of moles of the compound you've been given. What I mean by that is you will be given a mass of something. It won't be the compound that you want, but of that compound, because we've been given a mass and the MR, and we can calculate the number of moles. Then we look at the balanced equation to calculate the ratio of the compound you want versus the compound you've been given. And then we obviously multiply up our number of moles. So if it's a 1-to-1 ratio, the number of moles will stay the same. If it's a 1-to-2 ratio, we multiply our number of moles times 2. So then multiply the number of moles by the ratio. And then we just use the equation. And in this case, it would be that the mass equals moles. So mass equals moles times the MR to calculate the mass of the compound you want. So that's the 4-step method then. These questions are all 3 marks, the ones that we've done here. Someone's asking, will the equation always be balanced? Yes. Unless they say it's not balanced, it will always be balanced. And also, you can always check. It's very quick to just check. I tend to always check just in case. But yes, they will always be balanced unless they tell you to balance it first. Okay, excellent. So we now know how to do that. Let's move on then. So now we're going on to empirical formulae, which uses elements of what we've just done. So it says here that a compound of iron and chlorine was formed by reacting 2.8 grams of iron with 3.55 grams of chlorine. We need to calculate the empirical formula of the compound. So before we go into how to do this, we need to know what the empirical formula is. So an empirical formula is the simplest ratio of elements in a compound. So for example, we know that carbon dioxide is CO2. And that is the simplest ratio that we can form. We could say it's C2O4. It would be exactly the same, but that's not the simplest ratio. The simplest ratio is CO2. And the empirical formula is simply the simplest ratio of elements in a compound. Now, there is a way to actually calculate that without using the ions like we have been doing, and it's with using the masses. So before we go into this, we need to know kind of what the masses are and what the equation is. It's the exact same equation that we've been using already. Someone's asking me, is this in the AQA syllabus? No, this is in the OCR and EdXL syllabus. But that's why I'm covering it just briefly, but it's not in the AQA syllabus. It doesn't hurt to know about it though, because they can ask it as an application question. So again, it uses exactly the same equation. So the equation is that the number of moles, equals the mass over the MR. So we've been given that there are 2.80 grams of iron, so that's our mass. The AR of iron is 56. So if we calculate the number of moles, then we do 2.8 divided by 56. So what's 2.8 divided by 56? Anyone know? Has anyone got a calculator? 0.05, excellent. So the number of moles of iron is 0.05. And then if we work out the number of moles of chlorine, it would be 3.55 divided by 35.5. So what's that? 0.1, excellent. Okay, so now we have 2 different moles. So we've got the moles of chlorine and we've got the moles of iron. And what we can see is that 0.05 times by 2 makes 0.1. So what that means is that in our equation, there is 1 iron for every 2 chlorines. So if we calculate it as a ratio, it's 0.05 to 0.1. So we make 0.05 1. There are 2 0.05s in 0.1, so it becomes 1 to 2. So that means there is 1 iron for every 2 chlorines. So the empirical formula of iron chloride is FeCl2. Good, excellent. Someone's asking me, should the ions method get the same result as the moles equals mass over molecular mass? Yes, it should. But in these questions, they will be looking at your method and they want to make sure that you can use the moles method. And also what can happen is, for example, the transition elements can exist in different ions. So for example, in this case here, we can see that this is an Fe2 plus ion. And the reason I know that is because, remember I said that the charges get swapped. So if this is Fe2 plus, and we know chlorine forms a minus ion because chlorine is in group 7, so it has 7 electrons. So that means it only needs to gain 1 electron to fill its outer shell. So when it does, it forms a negatively charged, 1 negative charge element, or sorry, ion. And then when they swap the charges, it becomes FeCl2. So traditionally what they do is they use the transition metals because they could form different ions, and then they won't tell you which ion it is. So you won't be able to use the ion method to calculate it. Can you check it the ion way of the elements? So you can, yeah, that's what I'm just covering. But with the transition metals, we often don't know what the charge is because remember, they can form different ions. So you can try and check it. So I know, for example, that this must be correct because we know that FeCl2 does exist. So all this is telling me then is that it must be an iron 2 plus ion, not an iron 3 plus ion. Good, well done. That's an excellent question. Okay, let's do the second example then. Okay, an oxide of lead was analysed. 0.414 grams of lead was combined with 0.064 grams of oxygen in this oxide. Calculate the empirical formula of this lead oxide. So again, we just need to calculate the number of moles of each. So we've got lead and we've got oxygen. So the lead, 0.414, so we do 0.414, we divide by the AR, which is 207. So what's 0.414 divided by 207? Great, 0.002, okay? So 0.002 is the number of moles of lead. And then oxygen is 0.064 grams, and we divide by 16. Now, I just want to clear up here that you might think oxygen goes around in pairs. So you might think, well, should this be 32? In the cases of empirical formulae, you always take it to be 1. No matter what's in there, you take it as 1. So we take lead to be lead on its own, we take oxygen to be oxygen on its own, because we don't know if it's going to be O2 in the compound. So remember, oxygen on its own goes around as a pair, but when it's used in compounds, you don't tend to find 2 oxygens. You will just find 1 oxygen usually. Great, so what's 0.064 divided by 16? Someone's asking, can you write that down? Because I will forget. What do you want me to write down? Sorry. So yeah, 0.004. Excellent. Okay, so this is 0.004. So what's the ratio then of lead to oxygen? 1 to 2. Excellent. So the compound then will be Pb as 1 and oxygen as 2. So PbO2. Great. So yes, okay. So in empirical formulae, I'll just write this down. In empirical formulae, we take every element to only be 1, ignore it. So we ignore the fact that some go around as pairs. And that is because in compounds, the elements do not always go around as pairs. Remember, we always take it, every element, to be 1. So that just means 1 times AR. Okay, all right, so that's empirical formulae. So content-wise, that's everything I wanted to cover today. So now we're just going to do lots of questions. So before I go over those questions, I'm just going to do a brief recap of everything we've covered to make sure that it all makes sense. So we started with the relative atomic mass, which we've obviously been doing a lot of now, either using them in the exam questions, which I should say they will usually give you. So although you have a periodic table, sometimes they want you to use specific atomic masses. So on your periodic table, chlorine is usually given as a whole number, but for example, in questions, they might want you to use 35.5. So they tend to give you the relative atomic masses in exam questions. We know now if there are lots of different isotopes, we multiply by the abundance or the percentage of that isotope in the Earth times the relative mass, and then we add that to all the different isotopes and divide by 100. So that's what we did here with rubidium and copper. Great. Then we used that to calculate the relative formula mass. So the relative formula mass, remember, is all the relative atomic masses of a compound or molecule added up. So we did magnesium fluoride. Again, they gave us the relative atomic masses. So it was Mg plus 2 fluorines. And same with calcium nitrate. What I was trying to show here is when we have brackets, we multiply by what's outside the brackets. So here we did nitrogen times 2 and oxygen, or 3 oxygens times 2, which gave us 6 oxygens, and then we added that to calcium. So they're the two basic things that we need to know, or the kind of the building blocks on which we do these questions. Then we need to know about the number of moles, which was the AR in grams. And we calculated using the relative atomic mass in grams, we calculated the number of moles. So remember, the key equation that we've looked at today is that the number of moles equals the mass over the relative atomic mass, or the relative formula mass. And remember that a mole always contains the same number of atoms, molecules, or ions, and that is Avogadro's constant there. So we did lots of different questions here, which was just using one compound or one element to calculate the mass or the number of moles. But in exam questions, they will ask you to do it using a balanced equation. And using this balanced equation, they will give you the mass or the number of moles of one compound, and then you need to calculate the mass of another compound. And it's about using the ratios of the balanced equations to make sure that we can do that. So for example, in if in this example here, they gave a mass of hydrochloric acid and we wanted the mass of copper chloride, we would use the equation moles equals mass over molecular mass to calculate the number of moles of hydrochloric acid. And then we would halve that, because the ratio of hydrochloric acid to copper chloride is 2 to 1. So we would halve the number of moles. And that means then that when we're using our equation, we would only use half of hydrochloric acid's moles to then multiply by the MR to give us the mass. And then we looked at empirical formulae, which we again use the same equation, moles equals mass over the formula mass. And we will usually have 2 or 3 elements in there, and we need to calculate the ratios of those elements to then be able to look at what the simplest ratio for the compound is. So for example, we did lead oxide, which we said that lead, the number of moles was 0.002, and the number of moles of oxygen was 0.004. So as a simplest ratio, that is 1 to 2, so it became PbO2. Okay, so that's everything we've covered today. Let's do some questions then. I should say that all the questions we've done today have all been exam questions, bar the kind of first few slides where we were looking at kind of the building blocks, but all the questions we've been doing for the past kind of 15, 20 minutes have all been exam questions, and all the questions I'm going to show you now are exam questions. Okay, so we'll start off with the first one then. We'll do one question and then we'll go on to the Q&A, and then we'll do more exam questions. So the equation for this reaction is that calcium carbonate goes to calcium oxide and carbon dioxide. So it's decomposing. The calcium carbonate forms calcium oxide and carbon dioxide. Calculate the maximum mass of calcium oxide that can be obtained by heating 25 kilograms of calcium carbonate. Okay, so I'll give you a couple of minutes to do this question then, and then we'll see what answers we get, and I'll go through how to do it. So the equation for the reaction is calcium carbonate decomposes to form calcium oxide and carbon dioxide. Calculate the maximum mass of calcium oxide that can be obtained by heating 25 kilograms of calcium carbonate. Excellent question I've just been asked. Do we need to convert the 25 kilograms to grams? Yes, you do. So remember the equation, moles equals mass over the formula mass, has specific requirements. The mass needs to be in grams. So remember that the mass is always in grams. And that's because the moles, remember that 1 mole is the MR or the AR in grams. So we can't do a kilogram. So yes, you need to convert 25 kilograms to grams. So if there are any questions about how to do that, feel free to ask. If not, when you've got the answer, just message me in the chat box and we can see if that's right. Okay, so first answer comes through saying 14,000 grams. Okay, I'll wait for a few more answers and then we'll go through it. Someone's saying 1,400 grams, 14,000 grams. Okay, all right, so the answer is 14,000 grams, and if you want to convert that into kilograms, you can, so it's 14 kilograms. For anyone that didn't know how to do it, we'll just briefly go through that now. So we've got the mass of calcium oxide, and we've got a mass of calcium carbonate. We want the mass of calcium oxide, so remember then, to do that, we need the number of moles of calcium oxide. If we look at our equation, We don't have a mass, but we have the MR, so we need the number of moles. To get the number of moles, we can look at the mass of calcium carbonate and calculate it using that. So the mass of calcium carbonate is 25 kilograms. In grams, that's 25,000. And then if we have a look, remember that the number of moles equals the mass, so 25,000 divided by the MR. So calcium is 40 plus carbon, which is 12, which makes 52, plus 48, which gives us 100. So it's 25,000 divided by 100. So if we do that, we get 250 moles. So 250 moles of calcium carbonate. If we look at our equation, it's 1 to 1. Oh, sorry, to 1. So that means that the number of moles of calcium oxide is also 250, and that's because the ratio is 1 to 1. So if there are 250 moles of calcium oxide, to calculate the mass, then we do 250 times the MR, which is 40 plus 16. So 40 in calcium, 16 in oxygen. So 250 times 56, which will give you 14,000 grams, which is 14 kilograms. So well done to everyone that gave me that answer exactly correct. Okay, so let's just do some Q&A. If there are any Q&A questions, I will answer them. If not, we'll do some more exam questions.
Cool. Yeah, if everyone could just pop any questions they have, I'll just answer a couple that were for me. Someone's asked, when are the rest of the tutorials from last week going to be uploaded to YouTube? Yeah, so apologies. I believe that there are 2 maths and 2 physics tutorials that haven't been uploaded. That was because of a technical glitch last week, so we're just waiting for them to be fully converted so we can upload them. And 3 of those will be uploaded by the end of the day today, and we're just waiting on 1 more. So sorry for the delay on those. And are there going to be Spanish lessons soon? Potentially, but we're not sure exactly when, so I can't give you an exact date. I wouldn't expect any this week or next week, but potentially after that, and I promise to update you as soon as possible. Are there going to be geography webinars? Yes, there will be geography webinars. I will check on whether we have a date for those, but I believe that those will be starting next week. Let's have a look. Yeah, a couple of questions, Aman. So could you go through the last question again? A couple of people have asked. And can you go back to the step-by-step from Mass's form equation?
Yep, so we'll go through the last question again, and then I'll go through the step-by-step as well. So if we have a look at this question, we've been given a reaction which is calcium carbonate decomposing to form calcium oxide and carbon dioxide. We need to calculate the maximum mass of calcium oxide that can be obtained by heating 25 kilograms of calcium carbonate. So essentially, we're going to heat 25 kilograms of calcium carbonate, and then we're going to form some calcium oxide and some carbon dioxide, and we need to know what's the mass of calcium oxide that can be formed. So if we have a look, we can use our equation moles equals mass over the molecular mass or the relative formula mass to calculate the number of moles of calcium carbonate. And the reason we do that is because if we want to calculate the mass of calcium oxide, remember our equation says that to calculate the mass we need the moles and we need the MR. At the moment we only have the MR. And remember, the MR is calculated by adding up the relative atomic masses. So to get the number of moles, we need the number of moles of calcium carbonate. So the number of moles of calcium carbonate is the mass, which is 25 kilograms. We convert that to grams because remember, moles are always given in grams. So that means when we calculate a mass, we have to do it in grams. So 25 kilograms to grams. Remember, there are 1,000 grams in 1 kilogram. So that means there are 25,000 grams. We then divide that by the MR, so that's the equation, moles equals mass over the MR. So we want the number of moles of calcium carbonate, so we've got the mass, we divide by the MR. To calculate the MR, we add up all the ARs, or the relative atomic masses of the elements in calcium carbonate. So calcium is 40, carbon is 12, so 12 plus 40 is 52, and then 3 oxygens, which gives us 48. So that gives us a total of 100. So calcium is 40 plus 12, 52 plus 48 gives us 100. So 25,000 divided by 100 is the number of moles, which gives us 250 moles of calcium carbonate. And then if we want to calculate the number of moles of calcium oxide, we use our reaction. So if we look at our balanced equation, what we can see is that for every 1 calcium carbonate that reacts, we form 1 calcium oxide. So that means if 250 moles of calcium carbonate react, 250 moles of calcium oxide are formed. So that means then we can use the reaction or the equation moles equals mass over mR. So we want the mass, so we rearrange this so that that then equals that the mass is the moles times the mR. So then the mass will be the moles, which is 250. The mR of calcium oxide is 40 plus 16. So there's calcium and oxygen in there. So 40 plus 16, which is 56. So it's 250 times 56, which is 14,000 grams. And if you want to convert that to kilograms, you can do. So remember, we divide by 1,000. Someone's asking about the answer for the second question. We will go through that in just a second. I am just going to go to this page here. So this was kind of the 4 steps that I give. So you calculate the number of moles of the compound you've been given. So just like we did then, we calculated the number of moles of calcium carbonate, and that's because we've been given the mass and the mR of calcium carbonate. We then look at the balanced equation to calculate the ratio of the compound you want versus the compound you've been given. So we've been given calcium carbonate, and we had a look at the equation. It was a 1-to-1 ratio, so calcium carbonate to calcium oxide. We multiplied the number of moles by the ratio. Well, the ratio was 1, so that means that then the number of moles stays the same. So it's 250 moles of calcium carbonate, which is 250 moles of calcium oxide. And then we use the equation mass equals the moles times the mR to calculate the mass of the compound you want. So the moles was 250, the mR was 56. So then we did 250 times 56 to give us the mass of the calcium oxide, which is what we wanted. So that's the 4-step method there. Okay, so let's do the second question then. So sodium reacts with chlorine to form sodium chloride. We've got a balanced equation there. Calculate the mass of sodium chloride that could be formed by reacting 9.2 grams of sodium with excess chlorine. So the first step is to calculate the number of moles of sodium. And why is that? Because we've been given the mass of sodium. We want the mass of sodium chloride. So remember, the first step is to, with the compound you've been given, calculate the number of moles. So that's 9.2 divided by the AR of sodium, which is 23. So that will give us a certain number of moles. We can then use the equation. If we look at our equation, there are 2 moles of sodium, or 2 sodiums, that react to produce 2 sodium chlorides. So it's a 2-to-2 ratio, which is simplified to 1-to-1. So that means if there are this many moles of sodium, there are that many moles of sodium chloride. Then to calculate the mass of sodium chloride, we do the number of moles, which is 9.2 divided by 23, times the mR of sodium chloride, which is Na23 plus 35.5. So if you put that into your calculator, you should get an answer. So what does everyone have for the answers to that question? Yeah, so a lot of 23.4 grams exactly. So that's the correct answer there. Well done. Okay, so remember that was the 4-step method. So we've been given the mass of sodium. So we calculate the moles of sodium, which was 9.2 divided by the AR of 23. We then use the balanced equation to see, well, what's the ratio of sodium to sodium chloride? We could see it was a 2-to-2 ratio, so effectively 1-to-1. So that means if there are 9.2 divided by 23 moles of sodium, there are that many moles of sodium chloride. To then calculate the mass, we rearrange our moles equals mass over mR equation to be that the mass equals the number of moles times the mR. The mR of sodium chloride, or the relative formula mass, is 23, which is the sodium, plus the chlorine, 35.5. And then we do this over here, we multiply them, and you should get an answer of 23.4 exactly. And it should be in grams. Well done. Okay, let's do one more then. So the overall equation for the Solvay process is sodium chloride plus calcium carbonate goes to sodium carbonate plus calcium chloride. The Solvay process, if anyone's wondering, is just the process of forming sodium carbonate. So just like the Haber process produces ammonia, the process is the process of forming sodium carbonate. So calculate the mass of sodium carbonate that could be formed by reacting 12.8 grams of sodium chloride with an excess of with an excess of calcium carbonate solution. That should say calcium carbonate. Just ignore that. Okay, so before we tackle this question, I want to say this is a 4-mark question, and I'm going to show why in just a second. So let's have a go then. So remember, the first step is to calculate the number of moles of the compound you've been given. So the compound we've been given is that there are 12.8 grams of sodium chloride. So the compound we've been given is over here. So the sodium chloride, the number of moles will be 12.8 divided by the MR. We just calculated the MR, but they've actually given it to us here, so it's 58.5. So what's 12.8 divided by 58.5? That'll give us the number of moles. You're not going to get a nice number here, but that's okay. So 12.8 divided by 58.5 is the number of moles. For the purposes of keeping the answers correct, I'm going to leave it as a fraction, and that's absolutely fine to do. So yeah, it's about 0.22. And then we look at the equation. So if we look at our equation, there are 2 sodium chlorides that form 1 sodium carbonate. So the reason this is a 4-mark question is because there's an extra step involved. So remember, step 2 is look at the equation and find the ratio. So the ratio here is 2 to 1 because there are 2 sodium chlorides forming 1 sodium carbonate. So what that means then is we need to do the third step. We need to multiply. So if we've worked out the number of moles of sodium chloride to be about 0.02, then we need to halve it because there are 2 moles of sodium chloride for every 1 mole of sodium carbonate. So the reason this is a 4-mark is because there's another step in there. We actually have to halve this over here. Great, well done everyone. Okay, so then if we halve that, so I'm just going to put a half in front here. We then, to calculate our mass of sodium carbonate, all we need to do is we take the number of moles, which we said is a half times 12.8 over 58.5. We then multiply that by the MR. So remember, the MR they've given us actually, which was nice of them, is 106. So we multiply that by 106, and that should give you your answer. So what's the answer then? Okay, someone's saying 11.6 grams. Yep, 11.6 is the correct answer. Great, well done. So hopefully that made sense. Before we finish, we'll do one more question then on empirical formulae. Well done to everyone saying 11.6. Again, that was a 4-mark question. The other questions we did were 3 marks. The reason it was 4 marks is because we had to change the number of moles because of the ratio in the question. Great. Why does it give us calcium carbonate's relative atomic mass? So they sometimes do that just because they want to make sure you've read the question carefully enough. All right, so they don't always tell you what exactly you need to use, so you need to make sure you read the question well enough. All right, we will just do this last question then on empirical formulae. So find the empirical formula of a compound containing 32 grams of bromine and 4.9 grams of magnesium. Someone's asking, if you miss one step, then will you lose all marks? No, so the exam schemes or the exam mark schemes always say error carried forward. So ECF means error carried forward. If you make a mistake, but everything else is correct after that, or what you've done is okay, then you get error carried forward. All right. If you follow the 4 steps that I covered, you shouldn't go wrong with these questions. They all tend to be kind of the same structure and the same style. So one empirical formula question. So remember again, the equation is that moles equals mass over MR. So for empirical formulae, we always calculate the number of moles of each element. So bromine, the number of moles will be 32 grams, which is mass over the AR of 80. So 32 divided by 80. So what's 32 divided by 80? Someone's asking me, how would you know what to round your final answer to? If they don't give you what significant places or decimals, always do it to 3 significant figures. So yeah, 0.4, well done. Okay, and then if we look at magnesium, it's 4.9 grams divided by 24. What's 4.9 divided by 24? Great, it's about 0.2. So this can also happen where it's not exact, but it is about 0.2. So then what's the ratio of bromine to magnesium? 2 to 1, exactly. So the empirical formula of magnesium bromide is Mg, 1 magnesium, so remember this is the 1, this is the 2, 2 bromines, so MgBr2. That's the empirical formula of that. Okay, excellent work today, everyone. Really, really well done. We'll be carrying on with the quantitative side of chemistry on Wednesday, where we'll be looking at atom economy and percentage yield as well. All right, there are some more questions on the screen that you can have a go at in your own time as well. Well done. Thank you,
Great,
everyone.
thanks, Aman. That was a brilliant lesson. Hopefully see you guys in another session soon. Just a reminder, we have maths at 11, history at 2, and biology at 3:15. So I'm sure I'll see some of you there. If not, see you in the next chemistry session, which is on Wednesday at 9:45. So thank you very much, Aman, for today's lesson, and see everyone soon. Bye.
Bye.